Okay, so let's talk about a chemical you've almost definitely heard of, serotonin. But we're going to go way beyond that simple happy hormone tagline and really dig into what makes it one of the most complex and honestly fascinating molecules in our entire body.
You know the drill, right? Feeling good? Oh, that must be the serotonin kicking in. It's the simple, clean story we've all heard a million times. If you're happy, your brain is getting a nice little serotonin boost. Sounds simple enough. But yeah, not so fast. Because if serotonin is just the happy hormone, then what in the world is it doing mixed up with anxiety? Or how is it in charge of your digestion or even your sleep cycle? The simple story starts to look a little shaky pretty quickly. And this right here just lays it all out. Serotonin doesn't have one job, it's got like a dozen. It's involved in everything: mood, memory, appetite, your body temperature, even how you feel pain. So, how can one single chemical wear so many different and sometimes contradictory hats? That's the big puzzle we're going to piece together today. To get to the bottom of this, we have to go back in time. And I mean way, way back. Because you've got to understand, serotonin isn't just some new thing in the human brain. It's an ancient messenger molecule with a history that stretches back billions of years. Seriously, serotonin was around long before brains were even a thing. In the earliest, simplest life forms, it was just a basic regulator. Then, as life got more complicated, it took on new responsibilities, acting as a growth factor that literally told cells where to go. It was only much, much later that it landed its most famous gig as a neurotransmitter in our brains. And that ancient history is exactly why, as Dr. N.M. Barnes puts it, this so-called happy hormone is actually involved in pretty much everything our bodies do. It's had billions of years to weave itself into the very fabric of life. Okay, so let's zoom in from that massive evolutionary scale to one very specific, very important part of the brain where you can see all this complexity in action: the hippocampus. So if you think of the brain's serotonin system as this huge highway network, the hippocampus is like a major city. It's a central hub that gets a ton of serotonin traffic, which makes it the perfect spot to see what this chemical's really up to. And what an important city it is. The hippocampus is where we process memories, where we attach emotions to those memories. It even influences our motivation and judgment. So you can see why serotonin's role here is a huge deal for understanding things like mood and how we think. And now we get to the big reveal. The secret to how serotonin can do all these different things comes down to a really cool and simple idea: a system of locks and keys. So here we are again, back to the central question. How is one little molecule managing our mood and our memory and our digestion and our sleep? Well, you ready for the answer? The whole thing starts with something called a receptor. All a receptor is really is a little protein sitting on a cell just waiting for a signal. You can think of it just like a lock. It's designed so that only a very specific key can fit inside and make something happen. And here it is, the big aha moment. Serotonin is the key. It is always the same, single key. But the effect that key has depends entirely on the lock it fits into. And it turns out there are tons of different locks or receptors. So the key itself never changes, but the lock is what decides what happens when the door gets open. So just how many different kinds of locks are we talking about here? Well, as you're about to see, this family of receptors is way more diverse than you'd probably guess. Get this. Scientists have found more than 14 distinct types of serotonin receptors in our bodies. That's at least 14 different locks for the exact same key. This is where all that incredible complexity comes from. Now here's the wild part. Take a look. These different families of locks can have completely opposite effects. When that serotonin key fits into a 5-HT1 receptor, it usually tells the neuron to slow down. But if that exact same key fits into a 5-HT4 receptor, it tells the neuron to speed up. Other types trigger totally different chains of events or just act like a super fast on switch. One key, so many different results. Okay, so why does any of this deep dive brain science matter in the real world? Well, it totally changes how we think about common treatments that mess with the serotonin system, like antidepressants. A perfect case study here are the most common antidepressants out there, SSRIs. You've probably heard of them. Their main job is to make more serotonin available in the brain. So in our analogy, they're basically just flooding the whole system with more keys. that here's the puzzle that stumped researchers for ages. SSRIs boost your serotonin levels within just a few hours of taking one. And yet, people often don't start feeling better for several weeks. If the problem was just not enough keys, the effect should be almost instant, right?
So what's the deal with that time lag? Well, now that we know about the locks, the receptors, we can finally figure it out. Okay, so here's what's really going on. Step 1, the SSRI floods the zone with serotonin keys, just like it's supposed to. But some of the first locks these new keys find are special ones called autoreceptors, and they act like an emergency brake for the whole system. When they get overwhelmed with all the new serotonin, these brake receptors slowly, over weeks, become less sensitive. And as the brakes get weaker, the serotonin neuron is finally free to fire more often. It's this long, slow adaptation of the locks, this gradual reboot of the whole system that actually creates the therapeutic effect. That delay isn't a bug, it's the entire point. And that's the bottom line. Feeling better isn't just about having more of the key floating around. It's about giving the brain the time it needs to fundamentally change the sensitivity of the locks. It's a full system reset, not just a simple chemical top-up. Which leaves us with a pretty incredible question to think about. For decades, medicine has focused almost entirely on the key, on serotonin itself. But now we know that the locks, the receptors, are where the real control is. So the question for the future is, instead of just flooding the whole brain with keys, what if we could design smarter keys that only open very specific doors? That could lead to brand new treatments that are way more effective and have far fewer side effects. And that is the next frontier.